if this were a normal mechanics course for our graduate students, this lecture would be your first lecture. And we're going to develop the equations of Lagrange and Hamilton in more or less a standard way. We're going to do it, though, with something that is, I think, very important to have in any study of physics, and that is that we'll build the Lagrange and Hamiltonian using the mechanics, mathematics, of generalized curvilinear coordinates, we call GCC. You would ask what those three letters meant. Most mathematical physics courses will take you through some examples of OCC. Those are orthogonal curvilinear coordinates, and there's some very beautiful and special cases of orthogonal curvilinear coordinates that we'll be developing, actually discovering, when we do the chapter 10 of this unit 1, which has the complex variables. They name any analytic function of z, and it has a coordinate system associated with it. And I think that's really a neat way to rediscover these coordinate systems, essentially having them give to you free. But they, because of a special Riemann-Cauchy relationship, will all be orthogonal curvilinear coordinates. Very special case compared to this. In this formalism, you can take any old trashy coordinate system, just draw lines randomly practically, but certainly take any random functions and put them on top of each other in any number of dimensions and analyze them very efficiently. So we need to know this in order to augment this. So basically we have the French way of doing mechanics, the Irish way of doing mechanics. This is Riemann and Gauss, the German way of doing mechanics. So we're going to have three nationalities at least here. I'll bring in Russian and all of that for modern mechanics later on. So this is very very important for other work than just mechanics.
So by curvilinear, we just mean that the unit vectors carry angular dependence.
That's right. And the example we're going to use is the simplest one: polar coordinates in 2D. Okay. I'll give you a problem with spherical, so we want to get that started, since we use so many things in all of our courses that are spherical coordinates. Atomic physics is born in spherical coordinates in the normal way it's done. So what we're going to do is take the differential chain rules that we've already talked about, which is basically calculus 2, and use them to build coordinate transformations. And we're going to develop the idea of generalized velocity. Actually, if you have generalized coordinates, and you need generalized velocities, and you need something called the Jacobian. And in particular, a lemma about the Jacobian we call Jacobian lemma 1. These are all very simple results, but if we organize them well, this should go fairly quickly. And there will be a little bit of a hiccup as we consider second derivatives, as generalized acceleration, and a lemma that goes with them. Lemma 2 is not that much more complicated than lemma 1. Anyway, that sets you up for writing Newton's equations, that's F equal ma, in GCC. That's what we're going to do today. We're going to see how to do it, and then some of the power that you gain by doing this. What's the advantages of using this sort of, well, let's call it Teutonic formalisms. Now, there's some trickery that Lagrange uses to develop, but that's what we'll show, but it won't be too hard using those tricks to obtain F equal ma in the worst possible coordinate system that you could ever have. Now the base vectors and what we call cells and the metric tensors that we call, we've introduced those as well. We'll be done with the polar
Dr.
coordinates.
Harter, the equation F equals ma is in fact it's a coordinate-free equation, right? This relation doesn't depend on any coordinate.
We're going to turn that thing right there in any number of Cartesian dimensions into a general equation, which you see on the wall over there. The thing that we're really trying to derive today is this one up at the top first, then this one, which is second in the row here, next. And the idea of a generalized force will also be there. And then clever ways to write them. We won't get to this until unit 2 or 3. That is the full Germanic thing. It's kind of ugly and hairy, using Christoffel coefficients, things like that. That we will not discuss today, although we will be deriving them without naming them for the polar coordinate system. So that's what we're after. We're essentially after the heart of classical mechanics today. This is a day where I can die after this lecture and you will have essential pieces of knowledge enough to maybe pass the qualifying exam if you've been paying attention. Okay, so this is really a heavy lecture. Okay, and it's pretty standard stuff, but I've dressed it up with a GCC to make it a little bit non-standard, a little more powerful that you would find it in standard textbooks, even Arnold. Seems to drift over those pretty carefully. So we're going to learn today about the contra and covariant objects. They're sort of the duality that we've already seen with these two ellipses that are sitting inside of each other, obeying various kinds of scalar products. And we're going to find that Lagrange perverts the covariant, and then the next lecture, next week, we'll deal with Hamilton. Hamilton prefers to use the contravariant. This is being taking some artistic license because when these Lagrange and Hamilton things were developed, they did not know of the or use the Riemannian geometries. And let's see, as I say here, we're going to define something called the canonical momentum. I think I've already used that word, maybe without explaining it. Canonical force. This is all based on our horrible history in which the world was controlled by the Pope, at least part of it was controlled by the Pope. And so you know how Galileo ran afoul of that guy. And fictitious forces. We'll have a nice definition of that. And that's the real power of this, is that sort of stuff, which is a real headache, it sort of hurts your head to think about it. This will help make you at least be able to deal with that more efficiently. So let's remind ourselves of the equations that we already have, the ones that are identically zero, Lagrangian with respect to momentum, absolutely zero. We've already been through that. The equations that the first parts of the Lagrange equations that we have, and they're the ones that are at the top row over there on the wall. A partial derivative of L with respect to velocity. We're going to use another notation for that. Momentum, P, we'll be using that notation fairly soon. The Hamiltonian thing, the same thing. We're going to be doing that in the next lecture, not this time. We're getting mostly on the Lagrangian today. And this is the geometry of it, which we will not see that much of in the work that we do today. So it's off to the races right now using a differential chain rules. Now these are Cal 2 things that are not in the actual text. It's been the Boathouse lecture number 10, middle of it, 57 to 73, develops the concept of a chain rule differential, which you should be familiar with already, but if you're not, go back over that. Anyway, the idea is that a differential of some function of x and y is the sum of partials times the differentials of the independent variables, of which we're only going to have two here. It's going to be an x and y coordinate system, and over that coordinate system will be overlapping a polar coordinate that has relations of various kinds with the Cartesian, okay? And we could make a pornographic novel out of this, but we're not going to do that. But still, these are going to be overlapping. And the interest is to see, first of all, how do you deal with the differential of the radius and the polar angle as a function of the differentials of x and y? And then how do you do the reverse of that? That's very important, you see, because it's very easy to invert a differential chain relation, even if the functions were virtually impossible to analytically or conveniently express the inversion. Now, the inversion that I'm thinking about here of this equation, which is a very simple relationship that gives the definition of polar coordinates in that is, gives the Cartesian x and y in terms of the polar coordinates, but the inverse of that particular relation might be terrifically difficult. But the inverse of this matrix here, and that's the way to think about these relationships that involve partial derivatives of x with respect to r, x with respect to theta, y with respect to r, and y with respect to theta. That makes a 2x2 matrix for our two-dimensional thing. But in general, we're going to be talking about, well, right away, polar coordinates is 3. And if we're going to be going off and do space and time, that's 4. But most of our mechanics problems that begin in unit 2 are complicated objects with sort of joints that have coordinates attached to them, you see. And those are where generalized curvilinear coordinates are really needed, because both the r, phi, and the x and y are at all points except singularities orthogonal. But the coordinates you get from some device like the trebuchet, which is what we're going to be doing in Unit 2, are not orthogonal most of the time. In any case, that's the thing that we want to get. And of course, the inverse relation of this looks very different from that. That's a nice simple relation. This one's got this arctangent 2 here of y and x to give you that. And then this one is asking for the square root. Is it plus or is it minus? That's a much more complicated equation. Nevertheless, the differential relations, that's something that you can always invert if there's not a singularity. So those are things I want to talk a little bit about.
Like if u and v are, so in any coordinate system, is du by dv always 1 over dv by du? Like,
oh no.
Or is it only for?
Oh no. Partials don't play that game at all. The total derivatives do, partials don't. Remember that they're very sort of contrived, because what they're doing is holding constant all of the other independent variables that there might be in a list like that. Here, this is understood that when I take that derivative, I don't move theta at all, right? Well, because of that, you're not allowed to turn that over just simply. Instead, you've got to take the whole matrix, as we'll see, and invert that.
Okay.
This is called the Jacobian. I call the inverse the Cajobian. So we use the letter J is very common to describe the Jacobian. But the inverse, and I think you see them up there, the Jacobian I picked for the three-dimensional example is a 3x3 J matrix. And I think that's pretty standard. You'll see that the curvilinear coordinates, which are Q's, that's the notation that Riemann used apparently. And what does Q stand for? Well, one guess would be queer. And they do get pretty queer. I mean, you're allowed to make anything with these, any curves you want. You can start out and do the formalism
So-
until you run into some sort of singularity because you really picked really queer functions.
So in a curvilinear coordinate system, when you want to invert the total derivatives, you just take the inverse of this Jacobian matrix and multiply
Yes.
that with dx.
Yeah, this is a matrix inversion problem, turning it over. So you'll see over there on the wall again, we have a Jacobian matrix in which the Cartesian x1, x2, and x3 are on top, and the q1, q2, and q3 are on bottom, and those are all the all three squared combinations, all 9 combinations of those 3 things with those 3 things. And then the column of the Jacobian, as we'll see, makes what are called covariant vectors. Then if you invert the matrix, or you build this matrix first and invert to get this one, that's always possible, at least for the matrices. But whatever, you now see that the queer coordinates q are on top, and the Cartesian x1, x2, and x3 are on the bottom, and the rows make what we're going to define as contravariant vectors. So that's the other thing we need to define today, is the so-called big E vectors. They're called unitary vectors, but that name, as I say, is obsolete given that quantum mechanics uses it for something else. So here's the differential in a Cartesian in terms of the GCC. Now at this point we define a shorthand so-called dummy index notation. Whenever you see 2 indices repeated on the same side of the equation, it's understood that you sum over all the dimensions that are available, in this case only 2, because we have this one, say, being Q1 and this one being Q2. And then these are this plain old X, Y, and Z, okay, in time if we're going to go with a particle into 4 dimensions. And that's where Riemann geometry ultimately got used in a very famous way by Einstein for relativity, in particular general relativity. It's 1915, not 1905. 10 years ensued while I worked that one out. Now, when you're doing this on paper, it helps to draw a line between repeated indices. And I say do that if it helps you to indicate the summation. And it's okay on scratch paper, but we have a real difficulty doing this if you're doing your homework on a computer. We don't have something that can very often, unless you're doing a drawing program of some kind that will actually let you draw lines like that. So this is a little ruse that I say you do when you're doing calculations on your scratch paper or even on something you're going to turn in, but it's really hard to publish that. Okay, now, the idea of getting these GCC ready for mechanics, okay, the 2 things we have to do. We have to take whatever crazy coordinate system we have, and this one's not so crazy, it's polar coordinates, but we have to take a generalized velocity by taking a time derivative. We use a dotted notation for a generalized velocity with a dot over a q function, in this case r and theta. And as I said, we need a limit for the Jacobian for the velocity, and we're going to, a little bit later, do the acceleration as well. Velocity is pretty easy. The generalized velocity relation is the chain rule. That's the differential rule for getting the velocity, because all you have to do is go through with this equation and divide by dt. The velocity v super j. Now we're going to be very persnickety about these coordinates. It's a really unfortunate thing, which I just didn't mention as we were passing through on defining the differential, and that is that Riemann used superscript notation for these coordinates. And I thought about changing that and doing something about that. In fact, I thought very hard about it. In fact, I even defined coordinates that would be opposite to this with their indices down, and wouldn't have to have something that looked like exponents, you see. This is not q to the first power, this is not q squared, this is not q cubed. That's unfortunate. So if you want to square or cube a coordinate in Riemann's notation, you got to put parentheses around these damn things, and then put the exponent outside the parentheses up a little higher probably to make sure it's clear. The better thing to do is just not use Q notation if you could use something more common like R and theta. So, you know, in doing polar coordinates, you wouldn't use the letter Q very much because of all the extra writing you have to do. And if you're showing it to somebody, the confusion that results from having the indices be up where an exponent should go. But that's standard in all of the geometry books. Riemann just sort of set that pace, and we've had to follow it. So we're kind of stuck with that. And here where the differentials the same. Also for velocities, velocities have the same indice up, and we're going to be persnickety about this because the things that have indices up transform differently than the ones that are down. They're kind of like the bras and the kets in quantum mechanics. The contras that have their indices up, they're like holding their knives up in the air, right? And then the covariants are the people that, you know, keep their knives, you know, down below. Okay, they're nicer people, right? The contras are the ones that sort of do things like velocity and acceleration. The extensive variables usually have them down, but we'll get into that later on. In any case, we've got to deal with these indices up. That's all there is to it. So these are three notations for generalized velocity that you'll see used interchangeably. Sometimes I use a funny little V omicron for that. I've stopped doing that because I like to use that for frequency, but you know, that's kind of neither here nor there. There is a generalized curvilinear coordinate velocity as Riemann might have written it if he was talking about a time derivative. So that means that the velocities use the same Jacobian matrix to make a transformation from the queers to the Cartesians, or the inverse of this thing back.
Dr. Harter, is the last relation where x dot j is dxj by dqm times q dot
That's
m?
it.
Yeah, is that
And this one
coordinate
right here,
transformation?
same thing. That's this.
Okay, it's like transforming from one coordinate to another.
Yeah, once you've done the differential relationship, in other words, you've defined your that takes your q variables and converts them back to Cartesian, you also get your Cartesian velocities that way. And then the inverse equations also. So that's kind of what lemma 1 is all about. Lemma 1 says that the Jacobian you use for coordinates is the same as the Jacobian you use for velocities. That's pretty important because later on we sort of get confused about, you know, what can we do with these general coordinates that we might not be able to do with Cartesian. And this is showing you that at least as far as velocity goes, you don't have anything new. Okay? So anyway, this is defining Jacobian and Cajobian right here. This matrix gives each GCC, or whichever, I don't know why, this could be a Cartesian curvilinear coordinates, I guess, but whatever. Differential dx, or velocity x prime, in terms of these QE guys. Okay, so our example is this. Partial of x with respect to r, well, that's cosine theta. Partial of x with respect to theta, well, we have to differentiate the cosine and make the sine with a minus sign, leaving the r there. Okay, then y and with respect to r and y with respect to theta are that. Okay, so okay, so far so good for the Jacobian. But now, inverse, so-called Cajobian matrix is flip partial derivatives of this of this matrix. We're talking about now a matrix that involves Q's up and Cartesians down. Okay, same idea, and this would apply. Limit 2 upside down works as well. Okay, now inverse the Jacobian for polar coordinates. Okay. Well, we could go back and we could take the derivatives of the arctangent and the square root, but that takes a lot of work. This is usually done fairly easily, especially if it's 2 by 2. Okay, and this you ought to have in permanent random access memory in the brain. Okay, what do you do when you want to invert a matrix? Okay, well, first of all, you check to see it is invertible by seeing if the determinant A times D minus B times C is not 0. If it's 0, forget it. It doesn't have an inverse. So whenever our coordinate system reaches a singularity, that's one of the ways it can do it. It can have this thing blow up. So it's not possible to define the Jacobian. And it's also possible that you can't define the Jacobian, but you can define the Cajobian. So it can work both ways. Yeah.
What do you mean by saying the coordinate system could reach a singularity? What does it mean?
We'll see, but you should know where the singularity of the polar coordinates is. It's where all the coordinate radii meet.
It's r equals 0.
Origin. Yeah. Right? Things are pretty nasty there. It's a cone and it's, whoa! We're right there at the crossing. How do you define any calculus, right? Exactly that point. So that's where you'll find things blowing up. Okay? And you see that. You see that because the determinant of the Jacobian here is R. Right? If that goes to 0, that's singularity. So basically, when you take an inverse, the other thing is after you've found that the determinant is not 0, then all you have to do is switch the diagonal, leave the off diagonals where they are, but put a minus sign on them. Now, over there on the wall, which we'll talk about later, is all the theory of adjuncts and subdeterminants, minors, and things like that we'll use for bigger matrices. But for 2 by 2, and most of the matrices you have to invert on qualifying exams, and even my exams, are 2 by 2. So get that, make sure that you can do that quickly.
Dr. I have one more question.
Yeah.
So when we use polar coordinate system for a problem, we do know that there's a singularity at r equals 0. Does that mean that...
For polar.
Polar, yeah. So does it mean that we cannot... it would not make any sense to evaluate any quantity at r equals 0, or any physical quantity at r equals 0?
Well, in risk of getting thrown out of YouTube, let me tell you what happens in polar coordinates at the center. It's called a clusterfuck, because all of the vectors that you make are all being crunched into one little mess. You're out of business at that point.
The censors aren't happy, man.
Yeah, that's right. Not happy time. Yeah. Vietnam War at the r equals 0. So, yeah, the geometry goes to hell is basically what happens in all of these things. It's just that GCC are going to have lots of other kinds of singularities. There'll be singularities that live on lines, singularities that live on surfaces, singularities that live on hypersurfaces. All kinds of troubles, cusps and foldovers, and especially if you're dealing with chaotic systems and trying to make a map of them, you're going to have lots of singularities. Okay, so in any case, that's one of the ways you check to make sure you don't have a singularity in a certain place. Okay, so now one of the things is, and I always tell you this as a way to avoid errors, make sure that when you're building your Jacobian and you find your Cajobian, that you test your results to see if they really do give you a unit matrix when you multiply them, right? So, sure, that's a simple formula for getting it. It's hard to make a mistake, but You're in a hurry, you're nervous, sweat drops are pouring off of your face and onto your paper, making a mess. It's pretty easy to make a mistake doing inversive matrix in a hurry. So when you get it done, check to see that it really does work. And sometimes you'll be starting with a Jacobian and making a Jacobian. Same thing. Check it. Okay. Anything else on that? Oh, there is one thing. Formally, you can see it has to be. This is really important. This is where we're going to make the scalar product of covariant and contravariant vectors. That's what we're going to use this relation. Km sub j of j super j, and that's the other thing. Whenever you're summing over indices in this business, one of them has to be down, the other one has to be up. One of them has to be a contra, and the other one has to be a co. That we'll see what's really involved in that later. But in any case, you see this one has an index up in the denominator. That makes it have an index down when referring to the actual quantity. You see, this one has an index up to match that one, and this one has an index up to match the fact that I have an index up in the denominator. So writing matrices like that is something you have to get used to in this business, this Riemann business. But in any case, once you've gotten over that notational oddity, you will then have a sum, which I call a chainsaw sum, of a partial derivative of Qm with respect to Qn. These guys disappear. Now this is one of the things we did with that boathouse analogy for partial derivatives. So then you'll have a partial derivative of the coordinate Qm with respect to the coordinate Qn. Now it's pretty obvious if m is equal to n, that you're talking about something that is equal to 1. But what about when they're not equal? Well, just remember that having a partial derivative with respect to Qn means that you're going to hold constant all of the other variables, including m. Therefore, m is not going to move. Therefore, its derivative has to be 0. Make sense? So this identity is supposed to be self-evident as you've looked at the partial differential calculus. But if it isn't, make sure you understand what is being said here. Okay. So that's a formal relationship about these two being inverse to each other. Now, we have acceleration to do yet. That's more than one step. And the reason it's more than one step is because these coordinates are curved. Generalized acceleration relations are a little more complicated. It's curved coordinates after all, isn't it? Okay? So when we apply a ddt to something we already have, that's our velocity right there, that's our x dot right there by lemma 1, okay? We note that a derivative of a product is a sum of, well, for u dot v, it's the du dt dot v plus u, and then a derivative of the second law, okay? Well, this would be fine. I could just go ahead and forget all this if this thing were not a function of time. We're talking about total derivative here, so if this thing has any dependence on time, I've got to include it. So there are going to be these extra terms here that are multiplied by q dot. But if it turns out that the Jacobian matrix is a constant, like a rotation matrix, and you're not changing the angle, okay, we wouldn't have to pause here at all. We would just write, we would have a relationship for acceleration that was very simple. It'd just be a Jacobian multiplying the queer acceleration. But we've got to keep that. That's very essential for all of the curvilinear cases that we'll be treating. Okay, so What we're going to do is apply derivative chain sum to the Jacobian. We're going to say the derivative of this thing is equal to a sum over the velocities times the partial of this thing with respect to qn. And this is the velocity n. Okay? So we're going to get a thing that looks like that. Okay, but we want to try to make it a little simpler than that. We remember that I can switch these, right? And when I write the thing that way, what I can do is say, I'm doing the partial with respect to qm of this thing. Okay, this is a sum now over a queer coordinate n of the part which would become partial xj with respect to time. Okay?
So, Dr. Harter, we switch because the claim is the functions are continuous everywhere.
We claim that it's not a singularity,
Okay.
okay? And that's part of being continuous differentiable, at least a second order. Okay? So that's why I made a big fuss with the boathouse derivation of that along the chain rule. Okay? So, by chain rule for x, though, that just becomes x dot. This is q dot, right? So by chain rule, that's the velocity. So we have a partial q of the velocity, x dot, that is going to be equal to this thing. And that's lemma 2. Okay? These are the two important lemmas. We've just gotten this one, and we had this one already. It's sort of similar. This one, very simple to remember, means you can divide out the dots.
I have one question. Like, when you make it on the previous equation, where we had d by
This
dt
one?
of partial xj by partial qm, and then you basically want to use that
That's right.
implicit.
This is a function
Yeah.
of the coordinates.
Sure. Yeah. So
Okay.
then you introduce that qn coordinate. So here.
Now, it's also a function of the Cartesian, because remember there's a relationship somewhere between the Cartesian and these, right? So pick your poison. If you're really thinking of this as a function of q, I'm going to write it this way,
Okay.
right? I could go through here and use Cartesian. I didn't need that. What I'm trying to do is get f equal ma out of the x world and into the q world. So these are the two lemmas that I need. I don't need any more than that.
Like here you have partial dqn over there, and then you have total differential on top, like dqn by dt. So
Yeah.
is it
Yeah,
partial?
this is a chain rule of this function, okay? So this would just be, if this is f, this would just be partial f with respect to qn times dqn. Now it's with respect to time. This would be a differential, that's a derivative. So we're expressing it in a linear combination of all the derivatives. Oh, the queer derivatives, right? The q derivatives, okay? All right. So that's the part of this that's needed. This is our goal. Get this Cartesian, drag Newton screaming, kicking out of the Cartesian world and into Q world. That's what we're really after here. That's what a classical mechanics class is supposed to be. That and how you use it when you do get it. So what I'm going to do here, I'm going to use the kinetic energy quadratic form, which I think we all know and love. We're going to use the Lagrangian one, the one that's a function of velocity. And we're going to use our Cartesian force to acceleration relationship to pull this off. The trickery that's involved in this is fairly trivial. The real hard part of this is just thinking about getting things into form that makes us able to go forward. Now, we're at this point not just doing two-dimensional, we're doing it for any situation that has any number of dimensions, degrees of freedom we call them, we're going to have a kinetic energy that in general would be a full matrix combination quadratic form. No zeros necessarily for j not equal to k. We're not demanding that anymore. We're taking a general case here. So these things are like inertia constants that we're going to run into later when we do rigid rotors or any kind of rotor. But certainly with generalized coordinates, when they really get queer, they're going to be totally non-orthogonal. There isn't any reason why you're going to have 0 for off diagonal. You've been living a charmed life if you can get by with everything being orthogonal. So we're going to, drop that requirement. And we're also going to have this mass show up in the F equal ma relationship. So we're going to be talking about an acceleration k here. In the Cartesian world, it is simply the double derivative with respect to time. In the queer world, it's something else entirely. We've just shown with limit 2 that we have to
Dr.
worry
Harter?
about extra terms.
Dr. Harter, so in a curvilinear coordinate system, the M matrix would have even off-diagonal terms. Right? That's what it is.
Say that again.
In a curvilinear coordinate
Mhm.
system, the M matrix would also have off-diagonal terms, right?
Well, we have to derive what goes here.
Yeah, because
Yeah.
my question is, in Cartesian coordinate, M was a diagonal matrix where if you have two masses, the two diagonals represented the mass of the two
Mhm.
objects. So physically we could see what that M matrix stands for. But in a curvilinear coordinate system, I was just wondering,
Well, the one we're going to do first in Unit 2 is a trebuchet.
okay.
And the coordinates for it are absolutely non-orthogonal. And this number right here, we're going to use Riemann's notation for it. It's G mu nu. It's the metric. Okay? And if we're going to be doing relativity, we're going to use the G mu nu that goes with general relativity. And you know it's not orthogonal. They're curved all over the place in space and time. Okay? So the answer to your question is yes, 1,000 times over. This guy right here is going to be our metric. And it's not always diagonal. We try to make it diagonal after we get someplace, but it doesn't come that way. Okay? Now, I'll also need a multidimensional version of work energy, just to start talking about it. We have a Cartesian definition we've become a little bit familiar with in our review section. It's really time to bring in the queer cube M for this whole thing. So this is where it starts, right here. I'm going to say, I'm interested in a differential of work. And all kinds of ways to follow your logic into different paths at this point. But we're going to take a very short circuit to that, as you're going to see here. But you can see what I'm doing here. I'm simply saying that dx has got to be this partial x with respect to q. That's the Jacobian as we've defined it, with x upstairs and q downstairs. Summed over these q coordinates, and the Newton's acceleration goes there. Now, I'll bring up another requirement that I do want to keep on these, and that I'll mention later on. But basically, I want these in the Cartesian world to be constants. That's I've stated that yet, but look out for that. Okay? So another way to write this would be to say, hey, I've got a generalized force. I'll call it capital F, and uppercase F as compared to lowercase f, with its indices corresponding up and down with the queer Q coordinates. So we have a queer force, queer coordinate relation for differential work. And this is basically the same as what we've got up here. Okay? So, what we're going to do is we're going to say that this thing is just this much. I'm going to say that this is a differential relation that's true for all possible values of the various dq1, dq2, or dr, d theta, but this could go on for n degrees of freedom. I can set these things any way I want, and it's got to be right. Well, I'm going to set the qm, a particular qm, equal to 1. I'm going to make this a 1, okay? And all the others equal to 0. Then this is the equation resolves. They say, hey, you can't do that. You can't set that equal to 1. That's supposed to be infinitesimal. Well, okay, I'll set it equal to 1 in units of Fermis, 10 to the minus 15 meters, all right? It's very small. I set it that, and I'm calling that 1, okay? So that's the trick we always do with differential relations like that, is throw away all but one term. If you've got the arbitrary q's there, then it has to be true. Each term has to be true. Each one of the coefficients of the dq's has to be true.
So in this case, mjk would be determined by the choice of the coordinate system. That metric varies from one coordinate.
Just one of them. Just one of them. We're picking on them one at a time. Every one of the degrees of freedom has an equation like this. This is a list of equations, but they all have to hold. So that's a key step in this dragging Newton kicking and screaming out of Cartesian world. Okay? Well, let's look at what we've got here. And this is where Lagrange trickery begins. This is our relation, okay? Right here. What we're going to do with this, okay? Well, the trickery is a calculus trick. I see here a double derivative of something. Now, I'm referring to this whole thing. So this is where I'm going to demand that these guys, the Cartesian versions of the mass, these guys have to be constants. They can't be functions of the Cartesian coordinates. Later on, our metric that we're going to get in curvilinear coordinate world, it will be functions of all the coordinates possibly. This one, not a function of a single one. It's going to be a constant. So I'm treating this whole thing here as only having this guy as a variable. Okay? Then this thing b is just a coefficient of the Jacobian. All right? And that a dot dot b is the same as the total derivative with respect to time of a dot b minus a dot b dot. Okay, now b dot's not 0, so I got to keep that term. And neither probably is a dot. If it were a dot 0, we'd have a pretty simple thing here. We just go Newton's equation again. Okay? So here's the a dot b time derivative. There's b, and then I've got this thing. I've got b dot. This is b dotted by d dt, right? Okay? So here's b, it's a Jacobian. Here's a, it's this weird sum that gives us a force value, a Cartesian force value, it's Fj really, okay? And we're asking for the double dot of it, okay? That's what we will be working with here. And this right here is the a, what we would call a dot b, and then this one here is a dot b dot. Okay, so we've got two things that involve a dot, and then we've got one of them as a b dot. Okay? Now this isn't going to work if I don't take care of that. This says Cartesian M matrix, mass matrix, must be a constant for this to work. Now in little letters here that you can't read unless you get up close to the screen, I say bye-bye relativistic mechanics or quantum mechanics. Is that really true? And the answer is no, if we allow us to have all four dimensions. If we make quantum mechanics relativistic, I'm back in business. But we'll talk about that little issue later on. So, what we're going to do then is convert the partial xj, for example that one, to partial x dot j. So lemma 1, okay, says that this thing right here is the same as that thing. And then lemma 2 says that the derivative of a Jacobian is a partial with just the dot on top, not on the bottom. Okay? So that's pretty good trickery. We're almost done. We're almost done. We almost have this equation that's up on the wall over there, and lots of other walls around the world for 150 or so years. Okay? We're going to simplify these relations. Basically, these relations involve an m and then a vector quantity being summed over right here. Okay? And this is the other thing that I didn't mention is the mj ksb equal to jkjm. We discovered that that had to be true the first day we played with collisions. We demanded hermicity, symmetry. Okay, so I'm going to turn this into a partial with respect to some queer coordinate of the quadratic form. And this is a very simple quadratic form, just a sum of squares. Okay? So I'm going to convert this one to that. Then I'm going to convert this one the same way. See, I've got an x here. Here I've got an x dot here, but with an mjk. This mjk is sitting outside. Okay? So here I get a ddt of a partial with respect to q dot, this thing, and then I got a partial with respect to q of the same thing. And we recognize that as our kinetic energy, 1/2 mv squared. But a funny sum that involves all n squared terms, not just a diagonal. Only for Cartesian coordinates will we get away with that. Okay? That's it. Newton has been dragged. This is what I call the Lagrangian derivative equation. It's still got the force sitting outside here. The next step is to get rid of that. The real Lagrange equation has a 0 outside there.
So that okay, so that Fm can be written as partial dV by dq, like the way we define force in terms of the potential.
That's right. The way we defined that thing was a sum over Jacobian of Cartesian things that we have been using all along. That's right. And so we'd like to tuck that one in out of sight. We want to get this thing in a form so no Cartesian stuff is left. You've got to drag Newton all the way and have part of it still in the Cartesian world. Everything has to be in Q world. Okay? But this is already a very valuable equation. Already very valuable. I call it the four-wheeled garbage truck. Four-wheel drive garbage truck of classical physics. You can take this thing anywhere, drive it anywhere with a huge load of crap. Take a monstrous, horrible mess of equipment. Time-dependent, not time-dependent, whatever, weird coordinates. And this, you'll always be able to trust this. This is something that will work for just about everything. The next thing we're going to do, it's only going to work for these little perfect forces that can be written as potentials. But if you have a force that's got friction in it, all kinds of dirty stuff that isn't written so nicely as a potential, or even come close to being written that way, this will work. So this is one to remember. This is one to keep in reserve for problems that might otherwise be outside of the academic niceties that we are come to expect. And if you're in Jackson, you would be writing it this way. But we can do better. We can make it more elegant if we're willing to pay a price of this. And that price is the Lagrange potential equations for things that actually can be described by potentials. So here's another trick up Lagrange's sleeve is if the force is conservative. That's, you know, at this point in the political situation in the United States, I say, conservative, oh my gosh, I don't want to come near this thing. Horrible. But this has a different meaning, right? We'll talk about that meaning then. It means it can be written as a gradient. Okay, so the line integral of the thing, work integral, isn't path dependent. That's kind of a very special force. You've got to admit that. Not one that has a lot of any friction in it. Okay, and of course here's the physicist's definition of the force, if that in fact is a conservative force. Minus, remember, partial u with respect to q. Okay? So, if this is true, maybe I can incorporate this u with this t here. Oh, and I don't have to worry about this. You see, because, and I'm going to make another whereas here, the trick requires that this potential is not velocity dependent. If that's the case, then I can just stick this thing in there, and if I stick it in here too, just to keep them the same, it won't matter because the partial derivative of the thing I stuck in here is 0 with respect to that, the velocity. So no explicit velocity dependence of a potential will let you define a thing called a Lagrangian function, t minus u. So far we've only been working with t as a function of velocity. Mm-hmm. Now it's going to be functions of coordinates. So both of these things, functions of coordinates
so
in general.
This would not work for magnetic force, right? Lorentz force.
Well, we're going to have to treat that one separately.
Okay.
Yes, that's the whole thing, because that will involve vector potential. This is scalar potential. Okay? And yes, we can do magnetism relativistically very well. Thank you. But right now, we're just thinking about something to be written as a scalar potential. Then the Lagrangian is well defined. You have to change it for velocity dependent things. So this is a nice way to express what we've got. And it's time to use them. Okay? Now recall, P was defined as a partial derivative of L with respect to V, so this is not new. We already have this one.
So Dr. Harter, so the Lagrange defined his Lagrangian this way, like if the force is conservative, then L is defined to be T minus T.
Kinetic energy minus the potential. Yeah. Weird, huh? Again, that's relativistic quantum mechanics working there. That's what's causing that. But here I'm just posing it as a formality. Lagrange didn't know about relativistic quantum mechanics. He came up with this. Okay? So this equation right here, P dot equal partial L with respect to Q. That's kind of neat. To get the other one, you take the dot off of this one and put it there. So even somebody with a 1K memory like me, I'm good with this. I have a hard time, just immediately writing down that thing, or this thing, right? d dt, partial L Q dot, minus partial L respect Q equals 0. This takes care of that. This takes care of it. P dot, time derivative of momentum is equal, that's kind of like a force. That means if L is not a function of coordinates like we've been talking about, momentum doesn't change, right? So you already got a conservation law of this thing, which is one of the things that Hamilton would claim that he's really good at, given the symmetry laws. Lagrange has them too, if you write it this way. Okay, so far so good? Now, we have to go through a little more geometry. The covariant contravariant business. We have to take care of that. Okay? And here's where I actually show the polar coordinates with their terrible singularity. And the Jacobian, okay, which was made of the partial derivative of x1 with respect to q1. Well, that's x with respect to r. Here's x super 1 with respect to q2. That's x with respect to phi, the polar angle. Then you go through it again for the second row using y, which is x2. And then you look at this thing and you discover, and this is what's really neat, is that the columns contain a vector of the Jacobian. The columns of the Jacobian contain vectors that are being drawn here. These are vectors that grow linearly for number 2, but stay the same for number 1. These are the equivalent of the r and the theta, phi. We're using phi here now for polar angle. The r and the phi coordinates have directions, you see. If I turn phi up, I go this way, and I start out along that tangent there, you see. So these are, I was going to make what we call a tangent space, these covariant vectors. But meanwhile, there's these other kinds of vectors that you get by looking at the Jacobian. But now you look at the rows, you see. So these are kind of row vectors, which would mean they're kind of like the bra vectors that you have in quantum mechanics that point this way. And these are like the ket vectors that point this way. You see, they make columns. A little ket up at the top here that goes with number r and coordinate phi, you see. And here you do the same thing with a bra pointing this way. That's a row vector associated with the number 1 coordinate r. And now it's a contra vector. Contra means knife up in the air, okay? That's the duality that we're having to take here, because we're preparing this to work on the most god-awful coordinates that you could ever have, G, C, C. All right? So, we have this one using the inverse polar definition. If you want to just go ahead and actually work those partial derivatives out, that's what you need to know. But obviously, this is an easier way to go, is to write the x and the y as functions of the curvilinear coordinates. Now here's what they are geometrically. You see how these things are glued, sort of tangents to their respective coordinates? That's because they're partial of the x's and y's with respect to that coordinate. That's just showing where it's they're going to move. You're going to move if you jack up the value of the radius. If you jack up the value of phi, that's the where you're going to move. Okay? So covariant bases are always tangent to the coordinate at every point. So everywhere you go here, you take the partial derivative with respect to that coordinate. It's just going to be in the direction that is specified by that particular coordinate. Q2 right here, okay? Along Q2 equal a constant, Q1 can change. That's what the partial derivative of something with respect to Q1 would be. So this picture is just a schematic. You're seeing it happening right here, but it's understood this is a two-dimensional coordinate system. It's not orthogonal. You see, this is not a right angle right here. Okay, so having these vectors that point out where things go is very useful, and pointing out where they don't go is also important. This thing right here, these things are gradients. You see what you've got there? This thing is a gradient. This vector is a gradient of r equal a constant. So this vector has to be normal to the r a surface, r equal a constant surface, okay? This kind of, when you first see this, makes your head hurt. This is a very strange thing that you would think you would want ever have, you see. This thing here, E2, okay, the gradient of Q2 equal a constant, okay, it's perpendicular to the surface Q2. And then here's the surface Q1 equal 100. E super 1 has to be perpendicular to that. And that's what you're seeing right here, you see? E super R, okay, is normal, okay, to R equal a constant surface. Well, it just points along the radius. It doesn't do anything different than this one does. They are the same. But that's because this is an OCC. It's an orthogonal curvilinear coordinate. And with respect to R, it's almost like Cartesian. It's where you see this. This is very strange. These coordinates right here are perpendicular to phi equal a constant. Just like these are along the phi changing lines. That is, as phi changes, you go along this line, you see? So you really have to start thinking about coordinates in a different way when you deal with GCC. And it starts to look really strange with these guys. The contras are called contras because they're different. They are very different from the codes. The codes act like you expect. Contras are just the opposite. But you can see there isn't much difference except that these get bigger as you go out in R. These guys right here get bigger as you go in and reduce R. Okay, so this is this business of metric base vectors and the cells that make them up is really a very important piece of work. Okay, here's where I say it again. The E sub 1 is partial R with respect to Q1. E sub 2, partial R with respect to Q2. So that would be the phi. This would be the R. Okay, tangent. We're used to that. This is what we call the first differential form in differential geometry. Very, very useful, and you know, you feel good about this if you've been doing your Cartesian calculus pretty well. So Q1 varies, Q2, Q3, whatever else remain constant. Okay, it's convenient for extensive quantities like distance and velocity. Things that are measuring how big something is. Okay? These are more intensive. The contravariant QN matches the reciprocal cells. So these things we're going to have to get used to. The gradient of Q1. Partial derivatives that give you a normal instead of a tangent. The normal space to tangent space are pretty fundamental to this development. Okay? Now, the reason for these is that the co-contra dot products are orthonormal. E sub co, E co m, E contra n dot is 0 unless they're equal. And if they're equal, it's exactly 1. Because remember the partial derivative that I showed you before? That very important Jacobian inversion? That's what makes it happen. It's connected directly with that. Okay, there's something else we've got to deal with. This is the duality business that I talked about. We're sort of going Hamiltonian, Estrongian, and then Lagrangian, or vice versa. Actually, that's Hamiltonian. This is more like Lagrange. Okay? If I do a dot product of these two, that's called a metric tensor, a covariant metric tensor. If I do this, I just get the one we're all happy and used to, the invariant Kronecker unit tensor, 1 or 0. This one got lots of off-diagonal components in general. For our thing, it doesn't, because we've got an orthogonal curvilinear coordinate system. But these two are inverse of each other, just like the Jacobians are inverse of each other. So that relationship, this thing with partial r's upstairs and the q's squares downstairs, this with the squares living upstairs, Cartesian in the basement, are inverse of each other. This is where we have the two sharing. That's really very simple. And that's the real reason it makes these things computationally powerful. You can do all of the stuff that you did with an orthogonal coordinate system and still have this messy thing that has some physics in it, like a bunch of wave fronts or something, making cusps all over the place. It becomes a very powerful method for analyzing things like that. So the polar coordinate examples, we've already seen the Jacobian giving its covariance, that is contravariance coming out of the Jacobian. There's what's in between the two. So here is the metric tensor. Okay, GRR is just ER dot ER, covariant. The contra RR is the contra R's dot in respect. Well, there isn't much going on here. There's a 1R squared and a 1 over R squared for that one. So polar coordinates, not much activity off diagonal. Nothing going on off diagonal for it. Okay. So if we're going to have a Lagrangian definition like this, we're going to have a relation like this for the velocity. Covariant E, Q dot. Q is contra, so I need to use the covariant E's in the sum. Okay? That's just the time derivative of the Cartesian vector R dot. Okay? When I put them together, you see how the metric comes up. Now this begins to answer your question. What was going to come into kinetic energy? Well, for a single particle, it's just going to be m times this would be the geometry. And I call this thing gamma mn, called the classical metric, a dynamic metric. Okay, so there's your Lagrangian. And the metric coefficients just reads it off for you.
So which means we can just interchange the order of E's and Q's so that we can write it as en times Q dot m times Q.
Yes, you sure can do that. I mean, you know, writing these two backwards better not make a difference, right? Absolutely. But here we only get diagonal terms, so you don't have much chance to make an arithmetic mistake. Okay? So here's what we're going to get. We're going to get m times r dot squared, just a 1, and this phi dot squared is going to have an r squared in it. Okay? So that's, you know, something that you already kind of knew. You knew that your kinetic energy had something like that in it. But this is getting it strictly from geometry, this differential geometry. Okay? Now once you have this, okay, I can define with the Lagrange equation. First Lagrange equation tells me what momentum is. Definition using each of the coordinates. Okay? I take this Lagrangian here and I take a partial derivative of that thing with respect to r dot. The definition up here on the wall says that should give me a p sub mu if I do a partial Lagrangian with respect to q dot. That's what we've got, partial L with respect to r dot there. So we're just using this definition of canonical momentum, first Lagrange equation that we derived before we even knew anything about GCC or stuff like that. Okay? And as I say, this one is not so surprising. Radial momentum PR is usual linear form. M R dot. Who needs it when you have a GRR that's just 1? It's not a function of any of the variables. But this one, wow! This is cool. P phi, partial L with respect to phi dot. Okay, that's m g phi dot. Okay, go through here and differentiate this thing with respect to phi dot. There's only one phi dot in there, and I get an mr squared phi dot.
That's standard one.
Angular momentum is what we just stumbled upon. This canonical momentum isn't just blessed by the Pope, it's blessed by whoever invented angular momentum, say Newton. That's cool, okay? Powerful. These are things that bug you when you first learn it in sophomore physics, okay? It's already got the moment of inertia in there, right? We don't even know what that means if we're big mathematicians coming through this avenue, right? Okay? Now, what about forces? Also wonderful, okay? We already did the momentum, okay? And this is just a slide from a preceding thing. I'm just breaking it, the flow here a little bit. The other Lagrange equation. Now I take the dot off of the coordinates, stick it on the momentum. P dot r equal partial L with respect to r. Okay, so I go through there, looking for r's in this Lagrangian. These are partials, you see. Okay, so I see an r there, and I see an r if I've got a potential. Okay, so I've got a partial u with respect to r in there being subtracted, and we always do that. And what I'm doing, what you're seeing is that I get the minus sign where it should be. This is like a kind of radial force, okay? And so, let me punch this thing so it doesn't die on it. This timer, obviously, it's warning me that I'm starting to go over time. Hey, stop that. There you go. Okay, this right here is the cool one, okay? And I say this is double wow, right? This is telling me that I'm getting an extra term here due to a partial r with respect to here. So I get 2r, and then we got a 1/2 times 2 is 1. I get mr phi dot squared, okay? Now p phi dot, if I look through here and try to find a phi, I don't find one, so I'm not getting anything. But maybe there's a phi in the potential. If there is, I'll get that. But if there isn't, if there's no phi in the potential, then this is telling me the angular momentum is conserved. Once again, a symmetry rule. Okay? Now, once you've got this, and you can see what this is. You see it's got mr phi dot squared. Okay? Mr omega squared. What you're talking about is either centrifugal or centripetal, actually. It's centrifugal forces fleeing the origin. Fleeing the origin if phi dot squared is positive, which it has to be. So that's a centrifugal force, mr omega squared. To sort of balance the angular momentum thing, which was mr squared omega. Okay, so it's all very nice bookkeeping that you're getting by doing this wonderful Riemann stuff. All right? Now, the thing you do now, and this is the hardest part of this generalized curved linear coordinate mechanics, is you say, okay, if that's p dot, if that's the total derivative of p, what I've got to do is go back to p, whichever p I'm interested in, covariant p, and take the time derivative of the bugger. All right? That means I have to take the time derivative of the metric tensor times this velocity plus time derivative, the metric times the time derivative of the velocity, which is acceleration, generalized acceleration, q dot, if you will. Okay? And then I am going to equate that to the p dot in this second equation right here. Okay, so that's where that's the rub. This is where it's not trivial, okay? I've got to do this. I've actually got to go and get my results out and do a time derivative, okay? So here's a p mr dot, okay? So p dot from that is this thing, okay? And then I've got this thing right here is also p dot, this thing right here, okay? So there we got equation of motion, okay? We've got centrifugal center fleeing force equals total centripetal center pulling force. That's what those have to be equal to. Center flee, center pull. Okay? Well, that's neat. The bookkeeping is cool. The bookkeeping is keeping track of things we already know. They're giving it to us in motion. This one is a little bit more weird, you see, because when I do P dot phi, I got to be really careful. I got three factors here. I got an m, an r squared, and a phi dot. If the m were actually changing, and I wanted to do a dot of this, I'd do a dot of the m, and then r squared phi. And then I got to do a dot of the r squared with phi dot times m. And then finally I got to do a dot of phi, which is just phi dot dot. So I would have three terms if m was changing, only two, because r squared and phi dot are the only variables that move here. Okay? And look what you get. Torque relates to two distinct parts, Coriolis and angular acceleration. Boom, as John Stewart says. We've got the whole mechanics that can be really a pain in the ass in sophomore physics. It's just coming out, boom. Which is good because we're certainly close to being done running out of film on the camera. Now, the interpretation of this, it's really cool. Weather. We're now experiencing south winds. We're sitting here as a low is moving in as we speak. And that low is turning as the Earth turns. The basic idea of the quantum mechanics behind this is that waves like to get in sync as close as possible, get the beating that's between them as slow as possible. So really what happens when air tries to rush into a low pressure area is it gets turned by the Coriolis force. This equation that we have here is giving, this is really what it boils down to, angular acceleration is -2 times r dot and phi dot. Being careful here to get the signs all right, but this is a cyclonic force. A low moves into Fayetteville, we get a south wind, and then a bunch of lightning and stuff because there's all sorts of condensation that's making the thunderheads below. And tomorrow we will have a north wind. And Legrand says it's okay. Is it okay with you? You be the judge. You are learning something that's not general public knowledge. But this is a very important basis of mechanics. This is the way you can use it. So I don't think I have to say any more. We've done what we did. These are Coriolis fictitious forces that we're talking about here. That's your weather.